Well, good evening. Welcome to Space Oddities. Thank you all for joining us on this Tuesday evening. Tonight, we have got a whole show dedicated to black holes. Now, we want this to be as interactive as it possibly can be. So if you have any questions about black holes, whatever they are, do put them in the chat because, we like to answer them. In my experience, having done lots of outreach with schools and things, when you talk to kids about what questions they want to ask, it's normally aliens or black holes they want to know about. So we hope that as adults, that desire to ask about black holes hasn't left you, and that you'll ask any questions that you may have. Just pop them in the chat at any time. Joined this evening by the usual suspects. Hello, Daz.
Hello, hello.
Hello, Roger.
Good evening.
Good evening. Hello.
Oh,
and goodbye.
Lou's gone.
Lou's popped off. Hang on, let's get him back.
Oh,
okay, there you are.
Just popping in and out.
How are you, Lou?
Doing well, thanks.
Good. And Thomas Henderson, who we've just learned, because we were wondering who was invading our stream. We didn't know who Thomas Henderson was. Apparently, he was the first Scottish astronomer royal, but otherwise known as Tom to us. So good evening, Tom. How are you?
Hello, I'm very well, thank you. Yes.
Great. All right, so this evening we're going to try and pack as much as we can into probably the next couple of hours about black holes. We're going to cover as much of the subject of black holes as we possibly can, but we're going to try and not overwhelm you with information as always.
It's already too late for that. It's already too late.
Yeah, absolutely. So we're going to take it a bit at a time, and please, any questions, any comments, put them in the chat. Let's just have a quick, before we start, let's just have a quick look in the chat. Who have we got? Hi, Jerry. Hi, Sandra. Hi, Aerospike. Hope you're all well. And Roger says, get ready, everyone. We're going into a black hole. In fact, we are going to start right now. So to kick off today, we're going to show you a short video, which lasts about 10 or 11 minutes, about the basics of black holes. Now, we have played this on the channel before, but quite a few of you might not have seen it. And even if you have, it's a bit of revision because we need a place to start with black holes. So I think we'll get the basics out of the way first because it's an immensely exciting, interesting subject, as you know. So here's just a video about the basics of black holes.
Black holes have long captured the public's imagination, mainly due to their mystery and popular perception that they are destructive, ravening beasts which destroy anything in their path. Films like The Black Hole and Event Horizon have perpetuated the idea that black holes are incomprehensible engines of destruction, dark destroyers of galaxies, the very embodiment of evil. The word black, of course, immediately invokes an image of something unknowable, dark, brooding. Black holes are creatures of the night, stirring our ancient primeval fears about the absence of light and its indelible association with death. Given these negative associations, it's hardly surprising that there is a whole plethora of myths and misunderstandings associated with black holes. Fed and amplified by popular media, these often drown out the actual science behind black holes. Despite the basic fact there is still much about them we do not understand. As astronomical objects, we do know a surprising amount about black holes. We know how they form, how they behave, and roughly how they work. We see the effect they have upon objects around them. We can measure how their gravity behaves exactly as predicted by Einstein. We have at least a basic idea of what lies inside them. So let us start our investigation by asking a basic question. How do black holes form? Astronomers categorize black holes into two main groups. The first is stellar mass black holes with masses ranging from around 5 solar masses up to 100. The second is supermassive black holes found at the centres of most galaxies, with masses which can be measured in billions of solar masses. There is no agreed minimum mass for supermassive black holes, which relates to what we know, or rather what we don't know, about their formation. The most massive black hole we've yet discovered is in the heart of a quasar and is designated TON 618. It has an estimated mass 66 billion times that of our Sun. Between stellar mass and supermassive black holes, it's believed that there is a population of so-called intermediate mass black holes. They should possess at least 100 solar masses. However, as yet we have no firm observational evidence for these objects, although logic dictates that they must exist. It seems unlikely that, in terms of mass, there are no black holes between 100 solar masses and the millions of solar masses we associate with the lightest supermassive black holes. Stellar mass and supermassive black holes are created in different ways. Let's see how. A stellar mass black hole is formed when a star with at least around 7 times the mass of the Sun ends its life in a cataclysmic supernova explosion. Blowing off its outer layers, the core of the star is crushed by gravity so much that its very atoms are squeezed into a tiny point and cease to exist as matter. The mass of the core is still present in this tiny point, which is known as a singularity. What is left behind after the supernova is an immensely strong gravitational field generated by the mass that the core of the star possessed, which we call a black hole. That mass is now concentrated into a point possessing, according to the maths, infinite density and zero volume. We do not possess the language to describe exactly what happens at the singularity, as all our laws of energy, gravity and time cease to apply there. The whole process from the supernova explosion to the formation of the black hole takes only a few seconds. Afterwards, the black hole is orbited by a spinning disk of debris from the explosion, which is known as the accretion disk. This debris is sucked into the black hole like water disappearing down a plug hole. Supermassive black holes are found at the centres of most galaxies. Their origins are hotly debated. With such vast mass, which can be up to billions of times the mass of our Sun, they cannot have formed in the same way as stellar mass black holes, simply because even the biggest stars have masses measured in only thousands of solar masses. We believe that there are two possibilities as to how they formed. The first possibility is that supermassive black holes are formed by the successive merging of stellar mass black holes. That is to say, two black holes of stellar mass merge, and the resulting black hole then merges with another black hole, which itself may be the product of a merger, which then merges with another black hole, and so on in a sort of hierarchy. After each merger, the resulting black hole has nearly twice the mass of the two that merged, eventually reaching what we would call supermassive. Here you can see how it would work. Stellar mass black holes merge to form intermediate mass black holes, which then in turn merge to form a supermassive black hole. It's worth pointing out that each merger may involve more than two black holes. There may be triple or even quadruple black hole systems which merge. We just don't know at the moment. While this idea for the formation of supermassive black holes sounds promising, it has a few problems. The James Webb Space Telescope, or JWST, has observed supermassive black holes in the infant universe existing in early galaxies just a few 100 million years after the Big Bang. These are all infant galaxies, as seen by the JWST just several 100 million years after the Big Bang. Each is thought to contain a supermassive black hole, which are too young to have formed from a succession of mergers because there simply wasn't enough time. It is believed that black holes can orbit each other for millions of years, very slowly and inexorably, drawing closer together until they merge. You can see that this would take an exceptionally long time to produce even a lightweight supermassive black hole, yet, just 700 million years after the Big Bang, the JWST has found a black hole with 40 million times the mass of the Sun. The figures just don't add up if we postulate that it was formed through mergers of smaller black holes. Perhaps a more likely explanation is that supermassive black holes were formed from the spontaneous collapse of giant clouds of hydrogen in the early universe. These clouds may have merged to possess enough mass for the cloud to exceed a limit known as the Tolman-Oppenheimer-Volkoff, or TOV limit, which is the maximum amount of mass an object can possess before it collapses into a black hole. Assuming these clouds of hydrogen were plentiful in the early universe, which they surely were, they could account for supermassive black holes forming so soon, in astronomical terms, after the Big Bang. It may be that both processes had a part to play in the formation of supermassive black holes. It's an area of intense research. One big question astronomers would dearly like to know the answer to concerns the relationship between a supermassive black hole, or SMBH, and the galaxy which surrounds it. Did the SMBH form first and then the galaxy then form around it, or did the galaxy evolve first and its centre then collapse to form an SMBH? At the moment we don't know because it's a sort of chicken and egg situation, but one intriguing fact has emerged during the last decade or so. A supermassive black hole can influence the development of a whole galaxy, controlling the rate at which new stars form because of the influence of intense jets of radiation emitted from the vicinity of the black hole. So there is a deep relationship between the co-evolution of a supermassive black hole and its host galaxy, which we are only just beginning to understand. Now let's turn our attention to the structure of black holes, which are probably the simplest objects in the universe. They consist of a boundary called the event horizon, and at their cores there is something known as the singularity. And that's it in terms of structure. The event horizon is not, however, a physical boundary. It's simply a place, a distance from the centre of the black hole, where any object crossing it can never leave again, because to do so would entail that object travelling faster than light. In a nutshell, it's the point of no return. Nothing beyond the event horizon can ever leave the black hole, including light, and this is why black holes appear black. What happens inside the event horizon can never be observed because no information can escape. This means that if somebody were to fall into a black hole, they could never tell anybody outside the event horizon what they saw. Because of this, we can never know exactly what happens inside a black hole. We have to be guided by theory only, with no way of actually testing our theories. The singularity should also not be thought of as a physical thing. Like the event horizon, it's a place rather than a thing. There, all our laws of physics cease to apply. Everything we currently know about time, space and gravity stops being meaningful. The singularity represents the place where all the mass of the black hole is concentrated into a point of infinite density and zero volume, and we simply have no maths to describe what happens in such a place. Obviously, talk of infinite density packed into zero volume does not sit well with astrophysicists, so we believe that in reality such a place does not exist, even though it does in Einstein's maths. To understand what is there, we need a theory of quantum gravity, which will unite Einstein's relativity with quantum mechanics. But relativity, which deals with massive objects behaving under gravity, and quantum mechanics, the behaviour of particles at the tiniest of subatomic scales, do not talk to each other. They are simply not compatible. A quantum theory of gravity still eludes scientists after many decades, but the quest goes on. We assume such a theory must exist because it's inconceivable that there are two sets of laws which govern the universe, one for large objects and one for subatomic particles. Somewhere the two must meet, and that is where we will find our quantum theory of gravity. It's like having two house keys of very different design, only one of which will open any single door, but knowing somewhere there is a door that they will both unlock. Until we have that quantum theory of gravity, what happens at the centre of a black hole will remain a mystery. Well, that's about it for now.
Okay, so that's about it for the explanation of the basics of black holes. Hope you enjoyed that. Any thoughts, team?
That was well done. That was exciting.
Very good,
Yeah.
Andy. Yeah, really enjoyed that.
Very
Very
well
succinct.
put together that was.
Glad you enjoyed it. Don't forget, viewers, any questions at all, let's see them in the chat. I haven't seen any questions so far, but we hope that you're going to ask some questions. There is one question that came from Aerospike00, who would like us to talk about Kerr-rotating black holes and black holes that have charges. Now, I think I will let you deal with that, Lou, in a little bit, if you would be so kind.
Thanks.
I thought you'd be impressed. Okay, I know you can. So there we are. All right, what we're going to do now is we're going to go on to this week's news, and funnily enough, the news this week is about black holes. So just give me a second to set this up, and we'll just talk about the news this week. Just some really interesting stuff about black holes in the news at the moment. There's been a lot recently. So let's have a look at the enjoyed that. Oh, thank you, Sandra. Thank you very much. Glad you enjoyed it. Okay, let's just get this maximized and let's have a look. Okay, So I need to get back to another place. It's all windows, more windows here. News for 30th of September does involve black holes. And just give me 1 second. I'm sorry about this. I've got a sticky mouse. Have you had a sticky mouse, viewers? Nothing worse than a sticky mouse. Okay, so let's get on with this then. This concerns new information about the black hole at the center of M87, an image of which is shown here. Now, you've seen this before. This is our first ever image of a black hole as imaged by the Event Horizon Radio Telescope Array in 2017. And since then, obviously, scientists have been studying it, and they've been extracting more and more information. Now, this black hole weighs in at 6.5 billion times the mass of the sun. And believe it or not, they've discovered it's spinning at roughly 80% of the theoretical maximum speed possible in the universe. To put that in perspective, the inner edge of its accretion disk, which is that glowing ring of plasma around the black hole that you see, that's whipping around at about 14% at the speed of light. And if you want to know how much that is, that's about 42 million meters per second. The researchers also looked at the magnetic field patterns around the black hole, which act like a roadmap for how material spirals inward. They discovered that matter is falling into the black hole at about 70 million meters per second, which is about 23% at the speed of light. Now, using these measurements, they estimated that the M87 black hole is consuming somewhere between 0.00004 to 0.4 solar masses worth of material every year. Now, that might sound like a lot, but it's actually pretty modest for a black hole of this size. It's operating well below what scientists call the Eddington limit. This is the limit of the rate that black holes can swallow material at, meaning that actually the M87 black hole is in a quiet phase at the moment, as you may know, the black hole at the center of our galaxy is in a sort of a quiescent phase. Perhaps most importantly, the energy from all of this infalling material appears to perfectly match the power output of M87's famous jet, that spectacular beam of particles shooting out at near light speed that extends for 5,000 light years. This supports the idea that these powerful jets are indeed powered by the black hole's feeding process. So this is all new information that we didn't know about this black hole before. What they've also done is to use a machine learning, artificial intelligence, and it's a type of artificial intelligence called dictionary learning, which thankfully you'll be glad to hear we don't need to go into here. They have looked at the original image, and using machine learning, they have managed to clean it up, if you like. So this is the image that we're all familiar with, that, as you may remember, was on front pages all around the world. This is the new cleaned up image.
Ooh, wow.
And as you can see, there are two main differences. Firstly, the dark area, which is known as the black hole shadow, that's the area where there are no photons, because any photons entering that area immediately get sucked into the black hole. So it's completely dark. There are no photons in there. That's called the black hole shadow. That has ended up a lot bigger as a result of the process. And the ring of material surrounding the black hole is a lot thinner. But, this is beginning to look now more like, your classic black hole that you might see portrayed in sci-fi and whatever. And and they say that they can actually do more with this image as well in terms of processing. Just in case you're interested, you'll see that in the image on the left, we have two bright spots in the material around the black hole, and one on the left. Now, those bright spots are produced by a process called Doppler beaming, and essentially it means that the bright spots indicate that part of the disk that is moving towards us, and the other part is moving away from us. So we can actually see work out the tilt of this disk as well. So that's quite interesting. And having refined the image, we get this quite nice bright spot in the part of the disk on the right that's actually moving towards us. And Doppler beaming, again, was not surprisingly a prediction of Einstein. They've also looked at the polarization of the light, because what they've discovered was that this is probably about a year ago, maybe a bit more. They discovered that the light coming from the black hole is heavily polarized, and I don't know what that's doing stuck in the middle. Just give me 1 second. I'm just going to get rid of this if I can. Give me 1 second and I'll just sort that. Okay. Right. That's a shame. Something has happened there. Right. Well, anyway, as you can see from the left-hand image and the right-hand image, the lines are the polarization of the magnetic field, basically. We're basically seeing the magnetic field. And what they found is that there's a really, really fine structure in these magnetic fields. And this is, as the theory goes, these magnetic fields at supermassive black holes are situated in a disk of plasma, or superheated gas, if you like, circling the black hole. These fields spin together into what are called magnetic towers full of incredible energy. And that energy in turn propels matters along the jets, which are stabilized by the magnetic fields and move at close to the speed of light. Now, these jets, and we know, as you can see, the jet coming from M87 in the image, that jet, as I said, is 5,000 light years long. And it actually emanates from a very small area outside the black hole. And of course, these jets have a big effect on the host galaxy. And what they've discovered here is that from 2017, when they did the first observations, and 2021, the image on the right, the magnetic field of the black hole has actually flipped over. Now, this was entirely unexpected, but there have been some big changes in the black hole's magnetic field in those 4 years. What does the magnetic field of the black hole flipping over actually mean? Well, nobody knows at the moment. But if you think about this, because these jets are ultimately generated by the magnetic field, what we're seeing is the flipping magnetic field obviously having an effect on the generation of the jet, which in turn is having an effect on the generation of the galaxy and the evolution of the galaxy and the star birth in the galaxy, which we've talked about before. So what you're seeing basically is a change in the magnetic field, which in some way is having an effect on the whole evolution of the galaxy, which is quite wild when you think about it. Okay, that's M87. Let's have a look at another bit of news that was in the news this week. This is a gravitational wave event dubbed GW 1904-12. So this actually happened in 2019, and when they first observed it. This is a black hole 8 times the mass of the sun colliding with another black hole that was 30 times the mass of the sun, about 2.5 billion light years away. The team observed uneven gravitational waves scattering in different directions, as detailed in a new paper published in the journal Nature Astronomy. But the mix of signals will vary significantly depending on where the observer is located with respect to the black hole recoil. Now, let's explain what that means. A black hole recoil is where you have 2 black holes merging, and the effect of merging, as we know, creates a new black hole, or a bigger black hole that's almost twice the mass of the 2 constituent black holes. And this gives it a sort of a gravitational kick. And the new black hole moves away like a recoil. Now, the speed of this has been determined, and the new merged black hole, if you like, is moving away at 31 miles a second. If this black hole is in a cluster of stars, that's enough for it to leave the cluster. We don't know whether this event took place in a cluster because it's too far away to see. But they also measured in what direction the resulting black hole recoiled as observed from the Earth and the system's orbital angular momentum. This is an amazing reconstruction of a cataclysmic event 2.5 billion years ago and will greatly advance our understanding of black hole mergers. It also helps to explain the existence of these so-called rogue black holes not associated with any star wandering the Milky Way. And they have no accretion disks, and because of that, they're not generating any electromagnetic radiation, no X-rays, no radio, nothing. One such interstellar loner, if you like, was detected recently by the Hubble Space Telescope about 5,000 light years away. And how do you detect a black hole when it's not emitting any electromagnetic radiation? Well, they did it through a process known as microlensing. And what happens is the black hole passes in front of a star, and the star gets dimmer and then brightens again. You need very sensitive equipment like they have on the Hubble Space Telescope to detect that change in brightness of the star. But this is known as microlensing, and it's the only way to detect these so-called naked black holes. It's estimated in the Milky Way, in total, there may be somewhere in the region of 200 million black holes. And at least some percentage of those are going to be wandering through the Milky Way, completely invisible to us, of course, as a result of the recoil from a merger. So that's really interesting as well. So there you have it. That's the news for this week. That's the black hole news, if you like.
And there's some news. There's some questions. Sorry, there's some questions in the
Sure.
the chat. I just pop up Sandra's question. Oh no, that's not the one. Sandra was asking why. How come there are black holes at the center of galaxies? I can't find the actual question. So yeah, what she's asking is how some of them are playing pareidolia.
Why are black holes? Right. Okay, Sandra, let me deal with that one. Why are black holes at the center of galaxies? Well, as I said earlier, you've got two scenarios. Either the black hole forms first and the galaxy grows around it, or the galaxy forms first and the center collapses under its own weight, if you like, to form a supermassive black hole. So we don't know which of those scenarios is true. It may be that both at some point are true, Sandra. We don't know, but basically it's an accumulation of mass that either precedes or follows the evolution of a galaxy. So Paul says, let's just bring this one up. Paul says, I think they found a black hole that isn't in the center, possibly due to a collision. Yes, I saw that as well. They have found a supermassive black hole that isn't in the center of a galaxy, and it may well be exactly what I've just been talking about, a recoil as the result of a merger. So yes, Paul, you're absolutely right there. Okay, any others?
Well, I think really what we should do is have a quick pop quiz, because I don't think they were paying attention, because I think they were playing the game of pareidolia, and they were trying to decide whether the image you had was owls or a pig's nose.
Right. Now listen, guys, you've got to pay attention, for goodness sake. Play the games afterwards. There'll be a test later. So
I thought it was Roger's nostrils, but
Yeah, when he's angry.
Right. If it means anything, Derek, I definitely see an owl. So and Paul. So there we are. Right. Can we get back to the science now? Is that okay with everybody? Okay. Let's leave the animals and get back to the science. So what we're going to do now is go to Lou. And Lou is got a really interesting presentation for us, as always. So let me just get that up on the screen. If you're ready, Lou, you ready?
I'm all set. Should be there for you.
Fantastic. Okay. Just give me a second.
While you're bringing that up, we had a question about Kerr black holes.
Yes.
And there's always someone who's going to try to ruin our show and ask questions like this. That's fine. That's fine. So you might divide the universe into two kinds of black holes. One is rotating, which would have angular momentum. That would be a Kerr black hole. And the other would be non-rotating, and that would be a Schwarzschild black hole. Okay. So, I'm just a poor planetary scientist. I'm not the highly paid, high energy physicist that Andy is. So I'm just keep that in mind.
I wish.
So a Kerr black hole is it's a mathematical solution, right, to Einstein's general relativity field equations, and it describes a rotating but uncharged black hole. All right, so it's named after its discoverer, Roy Kerr, in I don't know, 1963 or something like that. And so it differs from the Schwarzschild black hole, which is a non-rotating black hole, because it is flattened. It has an oblate event horizon, and a ring-shaped singularity, not a point source singularity at its center. It accounts for the Kerr metric, as it's called, accounts for the mass of the black hole and its angular momentum. And some feel that it's a more realistic model for a rotating black hole, which we generally observe in the universe. As you can imagine, if you have something that contracts quickly, it's going to rotate. So that's what I know as a poor, underpaid planetary scientist about Kerr black holes.
So,
right.
But at the moment, I think I'm correct in saying that every single black hole we've observed has been a rotating black hole.
Yes, I think the Schwarzschild black hole is a theoretical black hole. I'm not sure if they've ever been observed. But.
And what about the charge?
Well, I don't know, but if you have a plasma that is quickly contracting and therefore rotating, and therefore you have rotating charge, you will expect to have, and if it's a black hole, okay, you're going to be rotating super fast, you can expect to have one whale of a magnetic field and rotating charge.
There you are.
There you go.
I've got a question.
Well, thank you very much for that question. And thank you, Aerospike, for the question. Any more? Put them in the chat. We'll do our best to answer them. Okay, Lou.
I think Tom's got a question, Andy.
Oh, has he?
Yeah, I had a quick question, actually. Just, I guess, not sure if it leads on from what Lou eloquently explained there, but is there a possibility that if a black hole doesn't have anything that it can consume, can it consume itself?
It has consumed itself. It is a point source. And so the size of when we talk about the size of the black hole, we're talking about the event horizon. Andy, back me up or tell me I'm wrong.
No, you're absolutely right. You're absolutely right. Yes, in a very real sense, there's nothing to consume. It's the black hole has consumed itself.
Okay.
Okay.
Thanks.
Right.
Thank you.
Thank you, Tom. Okay, so Lou, over to you. From apples to black holes.
Well, I'm running out of titles is the obvious answer here. So. And I'm a bit confused. I said, well, okay, I'll describe black holes. Well, that's not enough. We have to go back further and look at the evolution of thinking about black holes. Well, that's not enough. We have to talk about the evolution of general relativity. Well, hell, let's just talk about gravity. What the hell? Let's just get the whole thing out on the table. So there's an evolution of thinking about this presentation as well. Okay, just to make a point. Let's see here. There we. How do I? Here we go. If my screen is not, if my window is not big enough, I can't change the.
Right, that's got it.
Yeah. Okay. All right. So The understanding of black holes is an understanding of gravity. And gravity has been a bit of an elusive quantity for thousands of years. Okay, so I thought, well, let's go back and see what the earliest thoughts in recorded history of gravity are. And it turns out that the Greek philosopher Aristotle is recorded as giving one of the earliest and most complete or comprehensive attempts at a scientific explanation of the motion of falling bodies by putting forth this idea that objects move toward their, and this is the phrase you want to remember, their natural place. Now I say scientific. This was science 2,000 years ago, not science today. 2,000 years ago, science was elegant. If you had an elegant explanation, it seemed like a good one. So Aristotle is trying to figure out why things fall. And he says objects fall because each of the four elements, okay, there's earth, then water, then air, then fire, have their natural place. And he encircles them around the earth, which was at the time the center of the universe. So things tend to want to fall towards the center of the universe or the center of the earth. And then surrounding the earth is a concentric sphere, which is the natural realm of water. And then surrounded by that is the natural realm of air, and then the natural realm above that of fire. So therefore, and this makes perfect sense, right? Earth sinks in water, water sinks in air, and flames rise above air. So that's the order that he put these things in. Everything gravitates toward its natural place. There's that phrase again in this model. And, it's fairly intuitive, fairly consistent understanding of the basic observations of how things work. So that's what Aristotle said. And in addition, he said, well, obviously, heavy objects fall faster than light ones. That just makes sense, right?
Mm-hmm.
Right?
Yeah, well, he did that.
Who would think otherwise? I mean, certainly not me. And this kind of remained the thinking for like 2,000 years. I mean, incredible. But enter Galileo. And so he wanted to challenge some of Aristotle's beliefs. So as we said, for centuries, followers of Aristotle believed in this idea of heavy objects fall faster than lighter ones because they fall through this viscous medium. But Galileo hypothesized and later demonstrated that all free-falling objects accelerate at the same rate in the absence of air resistance. And he correctly identified air resistance as the factor causing lighter objects, like, say, a feather, to fall slower than heavier objects, like a hammer. And by the way, the choice here in this example I just gave you of feather and hammer was replicated on the surface of the moon by Apollo. I think it was Apollo 16. They actually somehow slipped a hammer and feather into their lunar lander. I don't know how they did that. And they dropped it on the moon, and you could see they actually fall at the same rate. Okay. So Galileo wanted to measure this, and one thing he did was to measure this with inclined planes. It's difficult to measure things falling rapidly, as in dropping something off the Leaning Tower of Pisa. So he developed inclined planes so he could watch objects fall at a slower rate. And therefore, he was able to measure with greater accuracy their rate of descent. And it turns out that he used this interesting clock that had had water in this vessel. And then on the bottom, it had a very thin flute, and it would drip water into a pan of sorts. And then he would measure the weight of that pan to decide how much time had gone by to measure the velocity of these objects. Just absolutely fascinating and creative. I thought that was his water clock. Okay, so I mean, he didn't have the you Galaxy 5 watch like I have. So anyhow, Galileo discovered a mathematical relationship between distance and time for falling objects. And he figured out that distance is proportional to the square of the time elapsed. You're going to see this later on in Newton. He found that objects accelerate uniformly, meaning the speed increases at a constant rate over time. And he formulated the theory of universal gravity. His experiments laid the groundwork, right, for an understanding of gravity's fundamental properties, showing that it acts equally on all objects, independent of their mass or their chemical makeup. And his laws about falling objects were considered kind of the first real modern physics, because he did measurements and he applied it to theory. So he was a good guy and a smart guy. And I think we often overlook him. You know, he developed the telescope, and we understand that. But he actually came very close to defining laws of universal laws of gravity similar to Newton. Okay, so Newton and the scientific revolution. Here we are we're in the 1600s, and this is really where real science began. Real science, observation and theory come together and support each other. So Newton is famous for his universal law of gravity, which states that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional, and here's what we remember from Galileo, to the square of the distance between them. And this theory that was outlined in his 1687 publication Principia, or we call it Principia, but it's actually Principia Mathematica. It unified the understanding of gravity on Earth and in the cosmos. So Galileo is working with objects on the Earth, and he's figuring out why things fall on Earth and how they fall and at what rate they fall. But he didn't tie that into things like, why does the moon orbit the Earth, or why does the Earth orbit the sun? One of Newton's big discoveries was that the same thing that happens on Earth happens in the heavens. That gravity is a universal theory that applies to all objects. He said, or I'd say he proposed, that the invisible force pulling on an apple to the ground is the same force keeping the moon in orbit around the Earth and the planets in orbit around the sun. That was huge. That generalization was really important. The strength of this mysterious gravitational force is directly proportional to the product of the two masses involved. And we know this equation, F equals G m1 m2 over r squared. And it means that more massive objects exert a stronger gravitational pull. That seems to make sense, and that's what he observed. The force is inversely proportional to the square of the distance between the two centers, the centers of the two objects. And as the objects get further apart, the gravitational force between them weakens, right? So he unified Johannes Kepler's laws of planetary motion with Galileo's theory of falling bodies. And he published his laws in the Principia Mathematica. And that was in 1687. Okay. This is so exciting, isn't it? You've just never had so much fun in your life.
I'm riveted, though. Absolutely riveted.
I understand. I do. I do. All right. So from all of this, you've already put this together in your head. You say, I know what that is. That's the famous equation that every high school physics teacher teaches. Force equals the universal gravitational constant times the product of the two masses divided by the distance squared, right? Well, we haven't really discussed this constant G yet, have we? That is the universal gravitational constant. And interestingly enough, Newton did not develop that constant itself. He published the law of universal gravitation, understanding that such a constant was needed to form an equivalency. but he did not determine its value. So it was only a proportionality that he published. So while he correctly formulated the inverse square law and explained how gravity works universally, it was only in the late 18th century that a value for G was experimentally determined by, and maybe some of you know this, Henry Cavendish in 1798. And what I'm showing you here on the right-hand side is the experiment that Cavendish used to peg the value of 6.67 times 10 to the minus 11th Newton meters per kilogram squared, please remember that, for the universal gravitational constant. So his experiment used a torsion balance hung by a wire to measure the gravitational force between two sets of lead spheres. And that allowed for the calculation of the gravitational constant G. And by placing small spheres to a suspended rod and bringing larger stationary spheres near them, he would measure the resulting twist in the torsion wire. And from that, he was able to derive the gravitational constant. Cool stuff. And, these people didn't have Google to find out the answers. They had to come up with this on their own. I just think that's absolutely remarkable.
Mm-hmm.
Sometimes I call them the ancients, but whatever. I think people who came before us are just, I don't think we give them enough credit. So moving on with Newton, in 1728, he demonstrated the universality of the force of gravity with his cannonball thought experiment. Now, who else did thought experiments? Albert Einstein is famous for kind of just thinking about things and wondering how would this work and how would this make sense? And we're going to talk about that in just a minute. So in his cannonball thought experiment, which I think every physics teacher ought to teach, I don't teach it with a cannonball. I bring a baseball into class, and I tell my students I used to be a great pitcher. And, so, and I did, man. I had junk. I had a slider, a sinker, and okay. But in either event, in Newton's thought experiment, he imagined a cannonball on top of a mountain. Now, if you shoot that cannonball without gravity intervening, the cannonball should move in a straight line, right? But if gravity is present, then its path will depend on the velocity. So if it's slow, if the cannonball is moving slowly, then it will fall pretty much straight down. Actually, it's not straight, but in an arc. If it reaches the orbital velocity, if it goes fast enough, where the gravitational force equals the centripetal force, then it will orbit. It will orbit the Earth in a circle. Well, actually, in an ellipse, or a special case would be a circle. If it's faster than the escape velocity, there's the kinetic energy is equal to the gravitational potential energy, then it will leave the Earth's orbit. And so we just kind of sat around with nothing else to do and thought about these things. And it turns out that this has worked for us for 400 years, helping us send spacecraft into orbit and to help them leave the Earth's gravity for other places. Newton's theories were solid, and we have relied on them for 400 years, and they work. Mostly. But there were some problems. There were some problems with Newtonian gravity. Here are a few of them. Newtonian gravity asserts that gravity is an instantaneous force. This contradicts special relativity, right? Because special relativity says nothing, no energy, no mass can move faster than the speed of light. So there was a problem there. Einstein realized that. The strength of the gravitational force between two bodies is proportional to the product of their inertial masses, right? That's the force of gravity between them. But it also measures the strength of attraction between two bodies. So you have, which is kind of called gravitational charge. So both you have inertia, two bodies resisting coming together, and you have gravitational attraction, two bodies coming together, both a product of their masses. So the inertial mass is actually doing double duty, and that is a problem. They didn't know why that was the case. Under general relativity, by the way, this problem goes away. Another problem was that Newtonian gravity, Newtonian mechanics, can't describe the discrepancy between the theory and observation of Mercury's orbital precession. Here's a picture of Mercury's orbital precession here. It's not much. The perihelion, the closest point of Mercury to the sun, rotates by about 40, well, the difference between the Newtonian theory and the observation is about 43 arc seconds per century, so not very much. And if we go further, it also doesn't allow for black holes, gravitational redshift. In other words, the loss of energy of light coming out of a gravitational well, and it doesn't allow for gravity waves. Okay. So what else? Do I want to say anything else about that? I don't think. Well, okay. I guess I do. So Einstein was aware of these problems, and he concluded that Newton's gravitational equations are not strictly correct. He didn't say they were wrong, only that they're not accurate under certain circumstances. In fact, they work very well for slow velocities like we experience, even spacecraft, right? But anything faster than that really has a hard time being accurately described by these equations. So let's move on and see what happened after that. This is one of my favorite pictures.
Nice.
Those of you who studied Einstein know that famously Einstein said that his happiest thought occurred here. And this is a quote. He said, "I was sitting in a chair." He said this in German, okay, but I'm in English. "I was sitting in a chair in the patent office at Bern when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled." Well, think about that. I mean, you'll feel your weight once you hit the ground, right? But if you're falling, if you're in free fall, no atmosphere, just free falling through space, and let's say you have a ball with you, and you let the ball go, it will fall with you, right? It stays with you. You're essentially, weightless. You can't tell what's going on. And by thinking of someone falling, Einstein realized that it was impossible to distinguish acceleration from the pull of gravity. And working through the mathematical implications of this, he was clear that gravity was an effect that could be produced by a distortion of space and time. So in other words, the gravitational field has only a relative existence. Because for an observer that's freely falling from, say, the roof of a house or something like that, at least in the observer's immediate surroundings, there exists no gravitational field. He can't detect it. Now, if you're paying attention, this is reminiscent of Galileo's argument. If an observer lets go of an object, it will remain in a state of uniform motion with the observer. Now, of course, this is with constant velocity. This behavior is independent of their chemical or physical nature. And of course, air resistance is removed from this thought experiment. So the observer has, as long as he confines his observations to their immediate vicinity, in other words, he doesn't look at the ground, right? See that it's fast approaching. That observer has every right to interpret his state as at rest. So just as Galileo argued that experiments in a closed box cannot determine the state of uniform motion in that box, Einstein argued that experiments in a free-falling closed box cannot be used to determine whether the box is in gravitational field or not. And he called this the equivalence principle. Okay, so here's another way of looking at it. Here on the left, we have a person standing on the Earth, and there's an apple next to them, and they feel the weight of their body pushing against the gravity of the Earth at 1g, and they're kind of pinned to the Earth, and if they drop an apple, it will fall, and everything seems right as rain. But now take that person, put them in a rocket ship, way out in deep space, and accelerate that rocket ship at 1g. Now, there are no windows in this rocket ship, okay? So they don't have that access. As it accelerates at 1g, that person can't tell whether they are on the Earth and not moving, or in other words, in a gravity field, or if they are out in deep space and accelerating at 1g. So in 1907, which was 2 years after the publication of his special theory of relativity, his miraculous year of 1905, Einstein came to a key realization. Spatial relativity could not be applied to gravity or to an object undergoing acceleration. In his theory of special relativity, okay, which talked about how time and space change with different inertial reference frames of observers, he determined that the laws of physics are the same for all non-accelerating observers, right? That's the special theory of relativity, non-accelerating. And he showed that the speed of light within a vacuum is the same no matter what speed at which an observer travels. It's always the same in a vacuum. Okay, so as a result, see, this is getting a little involved, but just hang with me, guys, hang with me. As a result of all this, he found that space and time were interwoven into a single continuum known as space-time. You can't really separate them, right? The key here is to remember that this, under special relativity, it states that events that occur at the same time for one observer may occur at different times for another, right? There is no simultaneity of events. Or another way to say that is simultaneity of events is dependent on the inertial reference frame, or the relative velocity of the observer, and therefore time. And the two observers, since they are traveling at different inertial reference velocities, will not agree on simultaneity of events as they observe them. All right, so we're kind of starting to get an understanding of where this is all coming from for Galileo. I'm sorry, for Einstein. But let's bring somebody else into the equation, and that is Marcel Grossmann. Marcel Grossmann was a Hungarian, lived between 1878 and 1936, and he was a Swiss mathematician, professor, and founder of the Swiss Mathematical Society. Okay, and he was good friends and classmates with Einstein. And there's a story that Einstein used to skip math. He thought it was too complicated and not needed. Grossmann went to math class, and it turns out that later on, as Einstein is trying to develop his general theory of relativity, he needed the math. He needed tensor math and matrix math and differential equations math. And so he had to call upon his friend, Marcel Grossmann, who helped him out with this. Grossmann was an expert in differential geometry and tensor calculus. And he had the mathematical tools which provided a mathematical framework for Einstein's work on gravity. So it was, it made sense that Einstein would enter into a scientific collaboration with Grossmann. So they kind of helped each other. But it was Grossmann who emphasized the importance of a non-Euclidean geometry called Riemannian geometry, which is also called elliptic geometry, was a necessary step in the development of Einstein's general theory of relativity. So different math, different coordinate system. And he mentored Einstein in this and in tensor theory as well. And he introduced Einstein to absolute differential calculus. So Einstein was brilliant, and he was like an intuitive thinker, but the math came was very difficult for him. What else do I want to say about it? I'm not sure. Well, the culmination of all this is that their collaboration, Grossman and Einstein, led to a groundbreaking paper called Outline of a Generalized Theory of Relativity and of a Theory of Gravitation. These were published in 1913, and they were this was one of two fundamental papers which established Einstein's theory of gravity. So you need the math. So if you're not going to math class, get your ass to math class. You need it.
Quite.
Get your ass to math. Oh, yeah, I like that. Okay. All right, but this.
Hello, Lou. Can you hear us? Ah, okay.
Yes, I can.
I think we've lost Lou.
No.
Ah, okay.
No.
You're still there?
All right, I'm here. All right, so enter Karl Schwarzschild, a German physicist. He's known for providing the first exact solution to Einstein's field equations of general relativity. And he did this in 1915, which is the same year that Einstein first introduced the concept of general relativity, right? Special relativity in 1905, general relativity in 1915. So Schwarzschild's work generated a number of original concepts which bear his name, such as Schwarzschild coordinates, Schwarzschild metric, Schwarzschild radius, I'll talk about that in just a second, and the Schwarzschild black holes, as well as Schwarzschild wormholes. So Schwarzschild radius, this is this equation in the box here in the lower right, that the radius, the effective radius of a black hole, of course, black holes themselves are point sources, but the effective radius of a black hole to the event horizon can be calculated as 2gm. We know what g is. We would then measure or assume mass over the speed of light squared. So he helped to identify black holes and to identify their properties. Now, this other equation that I show you here, well, it's a little boring, but I can tell you a little bit about this. Okay, so the first thing is this r sub s in the denominator in the middle of the equation. That's the Schwarzschild radius. The dr squared, d theta squared, d phi squared, those are just spherical coordinates. And so I'm not going to ask you to do anything with this. It's the kiss of death to present any equation in a presentation. But the point is, it kind of makes it, if you sat with it for a while, it would make intuitive sense. And Schwarzschild is really the I won't say, maybe discoverer is the right word, of the physics behind the black hole. And I will end there.
Thank you very much.
And if you've stayed with me for this long, God bless you.
Yeah,
that's all I have
Thanks,
to
viewers,
say.
if you stay there this long.
Well done,
You're going to need to just top up your mental thinking, because the next bit is gets a bit wild. Anyway, no maths involved. No maths
Oh God,
involved.
don't do this to them again. They can't take it.
That's the end of the maths for today. But anyway, thank you, Lou, because we can now see how these ideas, you know, from the Greeks onwards, came together really with Einstein, but Schwarzschild coming up with the first solution to Einstein's field equations. The tragedy about that, of course, was that Schwarzschild did this work while he was fighting in the First World War at the German front, and he suffered injuries in the First World War that he later died from, and he died very young. And it was a tragic loss. Well, every death is tragic, of course, but his was a tragic loss to science, because I think he was only in his 20s when he died. But look what he gave us. Look, you see this on the screen. That's what he gave us, and from that, we get the ideas of black holes. Now, Daz is going to talk in a little while about how we know this and how we observed the first black holes and how it all came together. But thank you, Lou. That was absolutely most interesting.
So Schwarzschild gave us big moustaches.
Oh, you're very kind. What mustache?
Okay, well, listen, thank you so much to Lou. I suppose you've got to rush off now for your teaching, have you, Lou?
I've warmed him up for the rest of you.
We'll nail them. Don't worry.
Thanks, Lou.
Thank you, Lou. Hope it goes well. What we're going to do now is to talk about something related to all this. This was a nice introduction to it. What I'd like to go through now is inside a black hole. Now, we're going to talk about two things. We're going to talk about approaching a black hole, and then we're going to ask the question, what would happen to you if you fell into a black hole? What would be your experience? So let me just set this up, and we will see what we can see. Okay, give me 1 second. Hope you're all enjoying our black hole special, viewers. Keep the questions coming, because we'd love to answer them for you. So let's have a look and see what we can see. So this is called inside a black hole, and it's both outside and inside, actually. But let me just get to where I need to be. Okay, so you hear many, many stories about what happens as you approach a black hole and what happens inside a black hole. Now, as I said earlier, we can never know what happens inside a black hole. We can never experience it. We can never observe it, because no information. So if anybody was stupid enough to venture inside a black hole, they could never tell anybody else who was seeing what they were experiencing. So we have to be guided by theory only, because we will never, ever, as far as we understand it, be able to communicate with anybody or anything inside the black hole. So let's just have a look at this first statement. One from astrophysicists is that inside time and space swap places. And what I'm going to do to you is explain exactly what is meant by this. So bear with me. Any questions, put them in the chat. Okay, so time and space swap places. So let's start outside the black hole. Now, outside the black hole, you can think of space as being a highway. Outside the black hole, you've got choices on that highway. You can turn left, you can turn right, you can turn round, you can stop. And that's space. You've got choices in space. Meanwhile, if you've got a clock on the dashboard of your car, it's always ticking forward. You can't change that, unfortunately. You cannot change time. So the thing that's actually pulling you forward is time. You can change where you are in space, but you cannot change where you are in time. Now, if you move forward on the horizon, imagine you come to a set of toll booths. This is the event horizon of the black hole. When you go through the toll booths, you notice nothing different. Nothing changes. But the rules of the road have just changed. Once you pass through the toll booths on your way to the black hole, through the event horizon, the highway turns into a one-way tunnel. From here on, every lane, every turning, every ramp leads to the same place, the tunnel's end, the black hole's center, the singularity. Now, you still see your watch ticking normally, of course, and you still move through space, but your freedom has gone. All paths are forced inwards. No matter whether you try and turn left or right, turn around, it has no effect. All your paths are forced inwards. So what is now driving you inexorably onwards is not time, it's space, represented by the tunnel. So time, as the driving force behind your movement, has now been replaced by the tunnel leading you inexorably onwards. Mathematicians say, in effect, that time has become space. On the other hand, conversely, space has become time, because your freedom of movement through space has disappeared. No matter if you try and move left or right or exit the highway altogether, you travel in the same direction. So space has replaced time as the inexorable and irresistible force leading you onwards towards the singularity. And mathematicians say, therefore, that space and time have swapped places. Now, if you're confused by all this, don't worry, because that's perfectly normal. These are concepts that can be difficult to comprehend. It doesn't matter, because this whole business of time and space swapping places is merely a mathematical expression of what happens. Now, if we want to relate it to your experience, what actually happens, we can simply state this. After you cross the event horizon, your path both in space and time leads straight to the singularity. It's unavoidable, it's inevitable, it cannot be changed. Once you pass that event horizon, you are going to the singularity, and there's no power in the universe that can stop that. So now let's talk about falling into a black hole. And obviously, I hope this never happens to you. But let's talk about what would happen to a human being, what they would experience if they were to fall into a black hole. If you fall into a black hole, at first nothing seems different as you drift past the event horizon. Don't forget, the event horizon is not a physical thing, it's just a place beyond which there is no return. Your watch still ticks, your heartbeat feels normal, you don't notice any boundary. But then you look up. The whole universe above you, the stars, the galaxies, even the glow of the cosmic microwave background, has been squeezed into a distorted circle of light overhead. It's as if the entire sky is being forced into a shrinking window. This is the result of the warping of space-time by the black hole's intense gravity. It pulls everything together into a circle, and time and space are extremely warped here. Now, that light grows harsher. The colors shift towards blue and ultraviolet, brighter and more energetic, until it's no longer the gentle starlight you first saw. The starlight's been shifted and its energy levels boosted towards the blue end of the spectrum by the intense gravity. It's radiation. It's radiation, basically, dangerous, burning, and it's also lethal. That circle starts to disappear, recede from you, get further and further away. Around you, there's nothing. Blackness, silence. No light comes from beneath or behind. The singularity itself doesn't emit any light, as far as we know. It just waits. It's invisible, but it's in your future, and that will not change. As you plunge deeper, that circle of the outside universe shrinks tighter and tighter until it's no more than a point, and even that eventually vanishes. So your world ends not with a big explosion or fire, but your world ends in silence, darkness, and inevitability. Let's talk about things I think called spaghettification, which people seem to like talking about. So what do we say about spaghettification? It's the process, of being torn apart by the black hole's intense gravity through differences in gravitational potential between your feet and your head. But when would this spaghettification start, and how long would it take before you're torn apart? Now, assuming that didn't happen, that spaghettification didn't occur, how long would your journey to the singularity take? Now, let's assume for the purposes of this that we're talking about an astronaut 2 meters tall falling feet first. The answers to these questions are not what you might think. Well, the answers do depend on the mass and the curvature, or the size, if you like, of the black hole. It's worth pointing out that it's not the gravity of the black hole per se which spaghettifies you, but it's the difference in gravity between your feet and your head. Now, let's take the example of a black hole of 10 solar masses. 5,000 miles from the event horizon, you would begin to feel the gravity differential increasing between your head and your feet. And that would be a force of 1g, 1 gravity between your feet and your head, 5,000 miles from the 10 solar mass black hole. Now, that may not sound too bad, but that is actually like hanging a 200 kilogram mass from your feet. It's uncomfortable, but survivable. Then at 2,318 miles from the event horizon, that differential rises to 10g between your feet and your head. You would suffer catastrophic internal damage as your organs and tissues start to tear apart. At 1,000 miles from the event horizon, the differential rises to 100g. You are torn apart, and that's when your life ends. But the interesting thing about a 10 solar mass black hole is that spaghettification actually occurs outside the event horizon for a 10 solar mass black hole. However, if that didn't happen, I don't suppose anybody can guess how long your journey from the event horizon to the singularity would take. It would actually take 0.000066 seconds, or in other words, 66 microseconds. So your journey from the event horizon to the singularity would take just 66 microseconds. Now let's move it up a bit. Let's now compare that with a black hole of 4 million solar masses, or in other words, the same mass as the black hole Sagittarius A star at the center of our galaxy. Now, in this case, you fall through the event horizon, you don't notice anything. You don't notice any gravitational differential between your head and your feet. But 25.6 seconds after crossing the horizon, the gravity differential would rise to 1g. So that's that 200 kilogram weight hanging off your feet, 25.5 seconds after crossing the event horizon. And just when your brain is beginning to register that discomfort, half a second later, it rises to 10g. And just as your brain registers the excruciating pain, 0.71 seconds, you slam into the singularity. In this case, with a 4 million solar mass black hole, your transit time from the event horizon to the singularity was 26.27 seconds. So the journey would take longer, and you would survive for longer, but your spaghettification happens in the last fraction of a second before hitting the singularity. Now, let's move it up even further. We're going to ask the question, how fast are you moving when you hit the singularity? Now, that seems like it might be a kind of interesting thing to know, but unfortunately, it's a meaningless question. You see, velocity is always relative to an observer. Inside the black hole, there are no observers. But more to the point, there's no space-time to measure velocity with. Now, normally, space tells you where you are and time tells you when you are. At the singularity, neither of these ideas work anymore. The coordinates themselves fall apart. So think of space and time as a map. Every place on Earth can be located by giving it a latitude and a longitude. But if you go to the North Pole, those coordinates break down. Longitude lines all pile together, don't they? And east or west stop making sense. The singularity is like that, but far more extreme. It's not that you're at a point, it's just that the very system of space and time and coordinates and location ceases to work there. So asking how fast you're moving when you hit the singularity is a meaningless question, unfortunately. Now let's look at falling into the universe's biggest monster. Okay, so we're going to look at the black hole that's at the center of the quasar TON 618. This is the universe's biggest black hole that we've discovered so far anyway. It's got 66 billion solar masses. It's 66 billion times, the mass of the sun. It's consuming material around it at a quite astonishing rate. Every day, it consumes the equivalent of 28,638 Earths, according to my calculations, of the material surrounding it. Just think of that. Every day, that black hole is swallowing the equivalent of 28.6 Earths. If you want to put it another way, that's 2 sextillion tons per second, if I've got the maths right. So that's 2 followed by all those zeros, tons per second. This is an incomprehensible rate of consumption by the black hole. But that is not even the most monstrous thing about TON 618. The most scary thing about TON 618 is that it's 242 billion miles across. And I have checked this a few times, and it seems to be correct. 242 billion miles across, or if you like, 15 light days. It takes light 15 days to cross its surface. This is the biggest monster that we know of in the universe. How on earth did a black hole get this big? Oh, we haven't got a clue. Let's be honest. You can see the solar system there by comparison. The solar system is 0.001 light days across, and TON 618 is 15 light days across. So you can see what a monster this is. Now, when you fall through the event horizon of TON 618, the gravity differential between your feet and your head is tiny. It's not even noticeable. How long would you fall through the black hole before it were noticeable? Well, this is quite shocking. You would fall for 5 days, 5 full days. Now, and as you fall, you would still not notice any discomfort until the differential between your feet and your head rises to 1 G. That's that 200 kilogram weight hanging off your feet again, just 0.3 seconds before hitting the singularity, and increasing until the differential would be fatal just 0.055 seconds before hitting the singularity. So again, you'd be spaghettified in the last tiny fraction of a second before slamming into the singularity, having been falling for 5 days. So what would you see as you actually approach the singularity? Well, like asking what speed you're moving at, the question of what you would see is, again, it's a meaningless question. The laws of space and time we're familiar with no longer apply. The physics which allows light to propagate and form images no longer applies. The very idea of seeing something ceases to apply. If you could survive the fall into the black hole without being spaghettified and continue to live until reaching the singularity, it's impossible to say what you would see, because seeing something is the result of light hitting your eyes in a way which allows your brain to construct a meaningful image. But here at the singularity, there are no physics forcing light to enter your eyes at all. All of physics has disappeared, and the very concept of light may disappear as well, along with our familiar ideas of time, space, and gravity. So there you are. So that's what would happen to you if you were unlucky enough to fall into a black hole. I hope you enjoyed that. And Pauline says, so when you enter the singularity, is that when, hang on, let's put this up on the screen. So when you enter the singularity, is that when quantum physics takes over? Well, yes, when you get close to the singularity, definitely, Pauline. But, you know, as I said earlier, we don't really know what goes on there because we don't have the language to describe it. It's so totally beyond our normal understanding of time, space, and gravity, that until we have this quantum theory of gravity, if we ever have a quantum theory of gravity, then we won't understand. So, but we can say certainly that when you get close to the singularity, that's when quantum physics and relativity hopefully will meet. But you know, this is in the future, because we've been trying to find a quantum theory of gravity for many decades. Einstein, in fact, spent the latter part of his working life working on a quantum theory of gravity, and it eluded him, and it's eluded every mathematician of science since. Yes, Lou?
Yeah, a couple of thoughts. First, AeroSpike00 says, so your nervous system wouldn't even register anything before you pass on. Well, I suspect this is a lot like Einstein's happiest thought. If you are in free fall in a gravitational potential, well, you don't.
That's just see if you're awake, Tom.
So in your head, yes, that you'd notice, but otherwise you wouldn't. And the other thing I wanted to say is that you are describing this, Andy, from the standpoint of the person falling into the black hole.
Absolutely.
What about people observing the person falling into the black hole?
So
they will.
The people.
Yes, go ahead. Go ahead.
Well, a rather weird things happen from the point of view of the observer. Time would slow down, so they would see the person approaching the black hole, and they would get slower and slower and slower, until eventually they would stop altogether outside the event horizon.
Right.
And that image would be permanently frozen into space, if you like. You can never see anything cross the event horizon.
Isn't that remarkable?
In actual fact, what happens to the light being reflected off that person or that spaceship or whatever it is gets shifted towards the red end of the spectrum. So the image will get dimmer and dimmer and dimmer, and it would pass beyond the ability of your eyes to see it before the event horizon. But obviously, if you've got an infrared telescope or something, you would be able to see it. But the image of that person would be frozen there, and you would never see them cross the event horizon, because for you as the observer, their time has slowed down. For the person crossing the event horizon, their clock is still ticking normally, but the observer sees time slow down. Yes, Tom?
I have a question, probably a non-question, but I'm just thinking about TON 618, and I'm thinking that's pretty big.
Yeah.
How big must the star have been that formed the black hole?
It definitely didn't form from a collapsed star. We can say that it was no. Supermassive black holes may have formed from two possibilities. One is successive mergers, and each time two black holes merge, they get bigger, and that merges with another one, it gets bigger and bigger and bigger. But you need a lot of time for that to happen, a lot of time. When you consider that when black holes merge, they can be orbiting each other for millions of years before they finally merge. So you need a lot of time for that. The other way is the spontaneous collapse of massive clouds of molecular hydrogen, which collapse under their own weight directly into a black hole.
Oh, didn't know that. Right. Okay.
Yeah. And in fact, astronomers think they've actually seen the first example of this recently.
Oh, wow.
Yeah. So it's impossible for supermassive black holes this size to form through stellar collapse. It's just there's not enough time in the universe for that to happen.
Yeah.
But this is an exceptionally big black hole.
Yeah.
And to be honest, it's difficult to even explain that away by either of those scenarios. So there's something I would think, not that I'm an expert, but there's something I would think we're not understanding about potential ways in which black holes can be formed.
So would Stevenson, I can't remember the name of it, Stevenson 218, would that, if that collapsed, would that form a black hole? Yes. It would.
Yes, it's too massive to stop at a neutron star. That would collapse directly into a black hole. Yes.
Okay.
Without a shadow of a doubt.
Yeah. Yeah.
But Tom 618 is so massive that 66 billion times the mass of the sun. When the most massive stars in the universe, their mass is only measured in thousands of solar masses. So how do you end up with something that's 66 billion solar masses? Exactly.
It's
Exactly.
insane.
Okay. Mike says, do we have any idea why matter becomes so dense in a black hole? What happens to the structure of atoms? Lou, do you want to take that one?
Sure, I'll try. So as matter collapses, there are forces that try to push against the collapse, right? But in my world, in our world, gravity always wins, as we say. So the first thing you'll notice is that there's an electrostatic force, right? And the same force that keeps you from falling through your chair. And if there's enough mass, then you bypass that. And then you get into areas of degeneracy and Pauli exclusion principle. In other words, quantum effects that would push against collapse. But if you have enough mass, they will win against that, and the object will continue to collapse. So because you're collapsing into a singularity, I don't know what, other than the gravitational potential, I don't know what mass means at that point. And Andy, I'm going to hand that over to you, see if you have any thoughts.
Well, yes, because a black hole doesn't contain any matter. Okay. Everything that goes into a black hole, right down to the atomic level, is atoms are broken apart and ultimately reduced to quarks. They're broken right into their constituents. So as I understand it, the only particles you will ever find inside a black hole are quarks, because atoms are torn apart by the gravity. They can't exist. In terms of,
that's theoretical, and I think I agree with you, but that's of course theoretical. We don't
yes,
know.
absolutely, yes.
Okay.
Well, we don't know because we can't get inside one and have a look. But theoretically, you're right, Mike. Electrons and everything else in the atom, protons, neutrons, electrons, the nucleus of the atom is torn apart, as theory has it, into quarks, and you'll just have a massive super quarks, because matter cannot obviously be reduced any further, because the quark is the fundamental particle. Yes, Tom, hope that helps, Mike.
Sorry, I'm the one with the rubbish questions tonight. I can't wrap my head around the sheer amount of gravity that must be involved to tear things apart, because my very basic understanding is that gravity is a very weak force, but I just can't wrap my head around that at all.
Okay, all right, let's just take a step back with that. So if you think of the Earth, okay, where's the center of gravity of the Earth?
In the middle.
Yeah, that's right. That's right. Does that mean that there's a denser matter in the middle of the Earth than in the rest of the Earth?
Possibly not.
No. Well, I mean, it is, because we've got an iron core, so that's very dense.
Yeah,
but
yeah.
Assuming that the Earth with the same density throughout.
Yeah.
Gravity would still be concentrated at the center. That's why it's called the center of gravity. Yeah. We could talk about centers of gravity, but I'll cut this short. So basically, what about the sun? Now, the sun is obviously a hell of a lot bigger than the Earth. Yes. There's very strong gravity at the center of the sun. Would you agree with that? You can't get close to it. So you don't feel the strong gravity. Yes, you can't. Okay. You can't get close to the center of the sun.
Yeah.
So when you take a black hole, it's the core of a star. Yes.
Yeah.
You can get very close to it because it's only 20 or 30 miles across. But you feel all of the gravity that was in the core of the star much stronger, because you can get right up close to it.
Okay. Yeah.
And that's why the gravity is so strong.
Okay.
Yeah.
Okay.
Does that make sense?
I think so. Yeah, I think so.
We probably haven't explained that very well.
No, I think you have.
You can treat all spherical masses, the gravitational force, as coming from the center of those masses.
Yeah.
And if you have a mass that is sufficient, and you can compress that mass within what would be its Schwarzschild radius, then you have a black hole. That then it collapses to a point source, and then you have a black hole.
Yeah.
So you have essentially an infinite density.
Yeah.
Of what you might call matter.
So if you think of compressing the core of a star into something that's only 30 miles across, that's going to be a very, very strong gravitational field.
Yeah. Okay, I get it. Yeah.
Okay. Right.
Thank you.
That's my pleasure. Okay. Hope you enjoyed that, viewers. Let's move on.
Thank you, Lou.
Yeah, thanks, Lou.
Thank you both. That was fantastic. It was really.
Yeah. So the next thing we're going to have a look at, we're going to take this in two parts. Daz is going to tell us a little bit about the history of the study of black holes. If you're ready, Daz.
Yep, I'll just get it up.
Okay. And then after that, which is not too long, Daz will be doing the second part a bit later. Oh, time's getting on, isn't it? Sorry, Derek, we may go over the 2 hours tonight, but
just bear with me a second.
Yeah, sure. After we've done that, we're going to just take a break from black holes, let your brains recover for a bit, and we'll do the night sky in the gallery with Roger after this. So
can you all see that? Has that filled the screen?
No, that you haven't got the slides up. You haven't got the slideshow window up.
What?
No.
I thought I did. Let me just
answer Derek's question. Well, Derek says, hang on, let me put this up on the screen. If all the mass that gets sucked into a black hole gets destroyed, why does the black hole grow? Well, if you remember your E equals mc squared, Derek, energy and mass being equivalent, basically the mass is converted to energy, and mass and energy being equivalent, the mass of the black hole increases, and that's why they grow. So Ian says, what happens if you put Schrodinger's cat into a black hole? Is it still there? Yes and no. So there we are.
Very good.
Yeah. So there we are. Okay, Daz, you having problems? We'll go to Roger, I think. Roger, are you ready?
Yeah, well, it won't let me go big.
Okay. Daz is having technical problems. So, Roger, straight over to you. What's in the night sky tonight?
Well, we have got lots of things.
Oh, sorry.
No, I'm black hole free tonight, so we're working our way through into October. So we're currently having our first quarter experience this evening, leading on to a full moon, which will be next week. So good luck with that. So looking south at midnight through the week, we will notice that the summer triangle is now starting to diminish in altitude, and we're starting to see some of the winter constellations coming through. But almost overhead, we've got the Andromeda Galaxy, so that's all well and good. And not too far below it, we've got Saturn. So Saturn's still a good sight to see, although we still have a very thin tuning of the rings. But that enables us to see some of the transits of some of the moons that we can not normally see with the tilt plane of Saturn's rings. But during the morning, before sunrise, we've got the two bright, shiny planets of Jupiter and Venus. And those will be quite nicely viewed from about 3 o'clock in the morning onwards. So look out for those. Okay, so we're starting to see some of the planets there coming through, and we will hopefully later on this month I will be discussing a possible impression of a comet. But we've got the crescent moon, which will be coming out through. Well, it's actually at first quarter, but we've also got the what people like to say is a supermoon. It's the harvest moon for the 6th of October, so that could be quite good. So anyone wants to see that, it's only about 13% or 14% bigger, so it should be quite good. So we've got a little article here about Sea of Tranquility, and that's all about Apollo 11 on the 20th of July 1969. I can't see why we've got that coming through, but it's not as if it's an anniversary, but it's always nice to see. And if you're familiar with its location, you can, if you've got a good seeing and a high power telescope, see some craters named after the 3 astronauts from Apollo 11. So good to see that if you can. So we've also got a transit of Titan coming out through, and that's on October the 6th. So that would be quite an interesting thing. Some of the things that it does enable us to see, while we do have the narrow angle of the rings at the moment, but it still can be a challenge if you haven't got a very big telescope. And we have got Ceres coming into a brightening phase on the 2nd of October. I don't know if any people like to look at the minor these big asteroids that we do have about. It is quite good, and becomes a magnitude 7 on the 2nd of October.
It is
so
now.
It might be worth it. Yeah, sorry. And it's close to the constellation Virgo, so could be a good opportunity for successive nights of seeing it traverse through there, and perhaps get to some of the galaxies that Virgo is well known for as well. So,
and don't forget, when you look at Ceres, you are looking at a dwarf planet.
Like Pluto.
Exactly.
Yes, for Pluto.
No,
so
we don't say dwarf, we say mass challenged planet.
Okay, so we've also got the good opportunity of looking at the Andromeda Galaxy. That picture is mine, by the way, because the one that was in the presentation wasn't good enough. So we have, obviously, a lot of people have taken some pictures of this, and we have got 2 stunning examples in the gallery this evening. So spoiler alert for that. So we've also got some Orionid meteor showers, which runs from the 2nd of October through to the 12th of November, and reaches a peak up the 20th to the 22nd. So that's all thanks to Halley's Comet's tail. So there you go. Now you know where they came from, thanks to Halley's Comet. And some of them are traveling out to 70 kilometers per second, so they will burn up quite brilliantly, and hopefully, if they're big enough, might leave a little trail in the sky. So anything between 10 to 20 meteors an hour. So there is a good opportunity to get out there and have a look through and see some. And then we've got the harvest supermoon, and it's 14% larger and 30% brighter.
Wow!
But on the whole, people will generally not know much about it and say, "Oh, look, there's a nice big bright shiny moon up there." So no doubt it will be mentioned as the days get nearer towards that event. So that will be next Monday.
Right, great.
So we've also got the Moon and Saturn coming together on the 5th of October, and they will be 3.33 degrees apart. So good opportunity for another little photo opportunity there, and they will be just there for just that brief time to get that close. So other notable stars and constellation: Polaris, the North Star. Okay, so we're obviously, if people are liking to see some of these things like the Pleiades or Cassiopeia or Cygnus, which is now starting to set in the north or into the southwest horizon, we were gradually getting to see the end of that, with an opportunity to see Mercury in the evening. It's now getting further away from the sun, so it will become easier to see, although it is still quite close to be a bit dangerous to actually spot it trying to use binoculars or a telescope, so be warned. But anything from early October start to look after sunset. That's about half an hour, but you will need a good low horizon to start to see it, and it won't look very big, so you might need to be very careful trying to spot it. Okay, so we've had the Orionids, we've now got the Draconids, which will also be coming through, so this could be confusing on what meteors we're actually looking at. But this was from the comet 21P Giaboccini-Zinner. Well, there's a mouthful. So
I do.
there we go. So
who discovered comets didn't have such inconvenient names.
Yeah, well, it's all the discoverer's fault, isn't it?
Yeah.
So there we go. So as the it seems to be quite a brief sort of shower. So between the 6th and the 10th is quite a short period to see these chances. But with the supermoon, it will become a challenge anyway, and they really need to be quite bright to get a chance of actually being spotted in the glare of the moonlight in the sky. So beware. And now we have got a mega super amount of people putting pictures in this week. I think because we had a smaller amount last week, people seem to rally round and it went a bit OTT this week. But nevertheless,
for which we thank you, of course.
Which we are most grateful. So we've got the sun in white light from Michael Murphy. He does like to contribute his solar images. This was taken on the 25th of September, so not too many days ago. And we can see that it is quite spotted. So well done for that. And we are starting to get aurora, though there was supposed to be some aurora tonight. Wasn't so good last night, but there is a threat of some aurora for tonight. So
yeah, they're predicting G plus, aren't they?
Yeah, so we'll wait and see. And Michael's also got T Corona Boreae, although this isn't actually flared up or anything. He's just managed to be able to get a cap. So we've got 20 minutes of totality of the image, and it's marked on this grid right in the center. So as you can see, it's not flared up at all really at the moment, but he's managed to take a photograph of it to show its position. So it's well done there.
Yeah, well done indeed. Good work.
So he's managed to get a good overlay of the position of it to get an idea of where it is. So well done for that. And Michael has managed to get the Deerlit group with Stephen's Quintet, and he's managed to get 7 hours. And it is a crop as well. But here we go.
Nice.
So we've got the Stephen's Quintet in the 11 o'clock position there.
7 hours.
Wow.
Yeah.
Tom is
so
saying,
not all those stars are just galaxies there. As you can gradually start to study, you can see more and more and more. So well done, Michael.
Is that the Michael Deep Field?
Well, one of his many deep fields.
Okay.
Yes.
Yeah.
Okay. And then he's got the double cluster in Perseus, and this was over 3 hours with his ASCAR FRA 300. Oh,
that's nice.
Ooh,
and
That's
he's got some lovely star colors there as well. So
Certainly
well done
is.
on that. Mm. Well done. Okay.
nice wide
Nice
field.
cat.
Yeah.
Mm. Now, Kenneth has managed to get a picture of the Milky Way with his camera and his Samyang 12mm, which is a lens that I love to actually shoot. And this is 15-20-second images. Have a look at this.
Oh,
Oh.
And you've got the magnificent Andromeda Galaxy up there
Yeah,
as
you
well.
have. Lovely.
Great grandpa's corn cob pipe.
Fantastic.
He's done well there.
Wow.
It has. The boy done good.
Mm. He did very good.
Yeah.
What is that?
Just using a camera and a very wide angle lens.
yeah.
What
Amazing.
is that? Andromeda up
Yeah.
in the
some
upper.
help.
It is.
Yeah.
Oh yes.
It has to be, doesn't it?
Wow.
Yeah.
Absolutely.
Gosh, that's
Absolutely.
really good. I'm jealous.
Mm.
Mm.
Jealous.
Now, talking of Andromeda Galaxy, here's one that Kenneth did with the his Olympus camera with a 200mm Canon lens and a 1.4 extender. So he's got 30 seconds exposures, and he's felt that he would like to dedicate this to a photographer on the narrowband channel on YouTube called Benjamin Chappell.
That's sad. I heard that.
And he
actually.
and he passed away earlier about a fortnight ago.
Very young lad.
Yeah, so this is the picture that he's done.
Oh, wow.
Look at that. Oh my.
Wow.
Just with a DSLR camera and a 200mm with a 1.4 converter on it.
Wow.
Stunning.
That's stunning.
Yeah.
Mm.
Look at those dust lanes.
Yeah.
Mm. All carefully processed in PixInsight.
Beautiful.
Well done.
Words.
Well done.
Well
Yeah.
done.
Well done, Ken. Yeah.
Beautiful.
Brilliant. Mm.
That would look
There we
really
go.
good as a framed photo on your wall, wouldn't it?
Mm.
I think he's already printed that one up on the wall already.
Right.
And why not? Right. So we've got Rachel and Jonathan. Yay. And this is 15 hours. Still only a fraction to what Tom does.
Yeah. Tom,
Of the Eastern Veil.
Yeah.
We probably spend about 15 hours on each channel knowing him.
I'm up to
And this is on
42
a
now,
little.
No Friday.
Right.
I'm up to 42 now.
Guys, life is short. Find something else to do.
Yeah,
Get a
well.
sea star.
And this is the result.
Whoa.
Oh,
Look at that.
Well, okay.
she's
That's
just
good.
showing it off now. She's just showing off.
Yeah. Yeah. Who
That's
needs 42 hours when you can do it with 15? You could do 2 more objects with that spare time.
I'll keep
And
that in mind,
I think Rachel just does this in Photoshop. She doesn't use PixInsight.
I think so, yeah.
So
well
the
done.
girl does good. She's amazing.
Yeah.
And then we've got our regular Lee, who likes to do the wide-angle Milky Way shots. And he's popped down to his local slate quarry again. And this was just a few nights ago with his Canon
always hanging
600.
around Slate Quarry, isn't
I
it?
know, he must be very dodgy character going around there all the time.
Yeah, absolutely.
And so he's managed to do some foreground exposures and night exposures and all the rest of it. So,
Oh, that's nice.
Oh, lovely.
Oh, that's lovely, isn't it? Wow, well
Mhm.
done, Lee. That's fantastic. Jesus.
that's
Absolutely.
about as vertical as you can get it.
Yeah,
Yeah,
yeah, I'm sure it is.
lovely,
Yeah.
lovely.
Mm. It's almost like the smoke coming out the chimney there.
Yeah. It's brilliant. Brilliant. Love
Yeah.
it. Love it.
Well done, Lee.
Mm.
And then Jerry's managed to capture the Andromeda Galaxy as well with his C-Star S30. Who needs an S50 when you can do it with an S30? And this is 3 hours.
Ha!
So you've been warned, Lou.
S30 did that.
Ah,
Wow.
That's very good.
That's very
That's with-
good, isn't it?
These little smart scopes are amazing.
Yeah.
Yeah, this S30 just gives you that little bit extra wider field of view, so you can get more of the actual galaxy in.
Yeah.
It's a stunning little machine.
Maybe given this, they should produce an S10, and can imagine what that would do.
Yeah, right. Just imagine what the S70 is going to be like. Wow.
So we can.
You'll have to do a 4-panel mosaic for that one.
Yeah. So there's
Probably.
a bit of an M31 competition going on tonight, obviously.
Possibly. Now we've got a few from Kevin. This is one that he's done, which is called the Question Mark Nebula.
Love this one.
And this is in Cephas.
Oh.
13 hours exposure, tough one to process. The O3 was very faint and took some coaxing out. But look at this.
That's
Wow. Look at that.
Kevin, that's fantastic.
Stunning, yeah, stunning.
13.
He does good. He does good.
Wow, 13.3 hours. I can't imagine that.
With a 4-inch refractor as well.
Yeah.
Unbelievable.
Absolutely.
I mean, that could be a Hubble image, couldn't it? Let's face it.
Well, it's done in the Hubble palette. So, yeah. Anyway.
I still want to do a yard. I bet we'd fool a few people.
Well,
I bet we would.
Yeah.
I expect you could. So there we go. Right. Onwards with Kevin's Venus occultation. We've got a few of the sequence here that we've managed to he's managed to capture. Some of which are quite atmospheric, like this one.
Oh,
that is atmospheric.
That's like a 30s B movie poster, isn't it? That's just amazing.
Now he's had to use the red filter on his camera to boost the contrast. Obviously, because it's daylight, you don't get that much clarity between the sky and the moon. So obviously, with the bright magnitude of Venus, it does help as well. But this was a few moments before, and then we've got it to come out the other side.
Wow.
That's great.
excellent.
Kind of haunting.
Yeah.
All we want now is American Werewolf music.
Yeah, I want to add some 30s B movie style typography on top of that and make it into a poster, Kevin.
Yeah.
Now the next images that we've got of Kevin are just a minute and about 10 seconds before the occultation actually starts.
Oh, wow.
That's gorgeous.
Look at that.
That's wonderful.
And when I was noticing, it was surprisingly how quickly it actually got closer and then disappeared so quickly. But he managed to have enough thin cloud there for the actual observation to be seen. So well done to Kevin for that.
Well done indeed.
Very good.
And then there's a picture of the sun. Some activity there, which was on the 28th. So just a few days ago. I've just rotated this round into a landscape format to give you a better idea of the activity that was on there. But that was on the western limb. And there were some quite interesting things. And then we've got a picture of the moon, which is also on the same day.
Who did that?
I did another one of mine. I've sort of gone for a
pretty
real
nice.
Very good, Rog.
a very impactful image to heighten all the details of the shadows, the craters, and things.
Beautiful. Beautiful.
And the surface of the different seas there to highlight.
Yeah, that's good, but you're always showing the same side. I don't get it.
Yeah, well, perhaps I need a sea star to see the other side. And then I was trying to do a Lee Hoare here, and out to a different venue here, and this is what I managed to get.
Oh wow!
Oh,
nice.
wow!
Look at that.
But I also managed to get a meteor in for some
You see, yeah.
miraculous meeting. So
Well done.
Did quite well there.
What was the exposure time on that?
That was only a 20-second exposure.
Wow. And you managed to capture
I didn't.
Video. Oh.
Yeah. I was just sort of shooting continuously to get all these. So
How many times have I sat there during the Perseids with the camera shutter open, trying to capture Amicia?
Feeling that, Andy. I'm the same.
Yeah, and it's happening everywhere that your camera's not pointing to.
Yeah, exactly.
Absolutely. So on that image, we conclude for the night's gallery. Thank you, everybody.
Wonderful.
Lovely images.
Right.
Wonderful.
Excellent.
So anyway, that was great, and honestly, I mean, what a lovely set of images. So there we are. Thank you so much, viewers, as always, for sending in your images. Don't forget, if you would like to contribute towards the weekly viewers gallery, it couldn't be more simple. You simply attach your image to an email, 1 image per email, please, and you mail it off to gallery@spaceoddities.space. That's gallery@spaceoddities.space. Don't forget, everybody who does contribute an image gets their own little gallery on the Space Oddities website, which, as you might know by now, is https://spaceoddities.space, and all the viewers' images are there. What we're going to start doing next week, we really love you to have your own galleries, and we're very happy to do that. What we're going to do next week, starting next week, is we're going to take our contributors' images on the gallery on the website and just run through them and show them off so that they get a bit more exposure. And we hope that you look forward to that. We're looking forward to that. So we'll pick somebody probably at random for the first one next week, and we'll have a look at their images and discuss them. So there we are. Okay, well, listen, time is getting the better of us this evening. So what we're going to do, we're going to carry on the black hole segment until next week. Daz is going to tell us about the history of the study of black holes next week. So you've got that to look forward to next week. In the meantime, what we're going to do now is we're going to go over to, I think we'll give Roger a rest for now. I'll swap round with you, Roger. We'll go next to Einstein of the week, and then we'll finish off with Constellation of the week. So it's been a bit quiet on the Einstein of the week front recently, but just give me 1 second, and we will just sort this out. It's been a bit of a bumper week for amazing amounts of idiocy, as you can imagine. Just give me 1 second, and we will get this up. So Einstein of the week this week is coming up right now. Okay. So, Einstein of the week, just 1 second. So many windows open here. What we want to do is go here, and then I'll just share that with you, and off we jolly well go. So, Einstein of the week for the 30th of September looks something like this. If you're not familiar with Einstein of the week, it's our weekly delve into the nether regions of social media to see what people have been saying about the universe. So the first one is...
Black holes have long captured the public's imagination, mainly due to their mystery and popular perception that they are destructive, ravening beasts which destroy anything in their path. Films like The Black Hole and Event Horizon have perpetuated the idea that black holes are incomprehensible engines of destruction, dark destroyers of galaxies, the very embodiment of evil.
Yeah. Okay, sorry about that. Let's start again, shall we?
Oh,
Deja vu. We starting again.
We've got
okay.
Andy is his own Einstein.
Yeah, definitely. So let me just try that again, shall we? So let's just share this. Okay. Okay, right, there we are. Einstein of the week. Okay. So Einstein of the week. This just made me laugh a lot because it's tragic in some ways. So this was a posting about the partial solar eclipse of the 21st, which obviously we couldn't see from Europe or indeed the States. And it clearly says where the partial eclipse was visible from. It was visible from New Zealand, Eastern Australia, Pacific Islands, and Antarctica, best viewed in southern New Zealand. Now, there were lots of posts in this thread to this effect. Probably not across England. So, you know, no, there was probably, is it visible across Bulgaria? Is it visible in Kenya? There were loads of them. But the amazing thing was the reply to this comment, probably not across England. This really did escalate quickly. Hasn't England already been eclipsed by the Muslim fraternity?
Oof, wow. Jeez.
I know.
Too late for him or her.
Yeah.
It's just unbelievable.
Rod, you're a lavvyhead. Get off.
Yeah, absolutely. I did reply quite pithily, as you could imagine.
Yeah.
So that was just unbelievable. Anyway, moving on. Next one. We have. Why is this not advancing properly? Come on. Right. I call this one Delusion Part 1. The Big Bang is a myth created by the Vatican. I bet you didn't know that.
Oh, okay.
Yeah.
Every day's a school day.
Yeah.
Leviticus something.
And then we go to, quite predictably, Delusion Part 2, which is talking about the Big Bang, super utterly satanically deceived nonsense, is how somebody described the Big Bang.
Wow.
So yeah, interesting.
That's got me worried.
Two different ends of the spectrum there.
Yeah, we got Satanism and the Vatican. Delusion Part 2.
War to end all
It's about the
wars.
Milky Way. There is no such thing as the Milky Way. Every planetary system in the universe is independent.
Oh, I forgot to read that paper. I'm
Wow.
sorry.
Yeah, absolutely. Yeah, I forgot that as well.
Wow.
And the next one is an example of when looking up into the sky really helps you. Can anyone tell me which direction to look to see the moon? I live on the East Coast.
Did you respond to that?
No, I didn't actually. Well, yes, I did. No, I did. I said, just look up. It's that bright thing in the sky. So there we are. And then the award for Einstein, in this case, plural Einsteins of the week, is all about day and night. Now, we know that day and night is not a difficult concept, is it? And this was occasioned by the posting of this image, which shows the Terminator across Europe and North Africa. Now, that's, you know, I think everybody agree that's an easy concept to grasp?
Yeah.
Okay. Are you ready for the comments about this?
Oh, my God. I dread to think.
Right.
No.
The next image I'm about to show is not that legible, so I'm going to read them, but let's go through them. I wonder how cool it would be if someone was in the middle of these halves. What do I have to do to live right in the division between night and day? Imagine being in a place half day and half night. I don't see the afternoon part. Must be insane to live on the border.
Oh, my God.
And how would for those who live, that doesn't make any sense. Whoever is in the middle of day and night must be thinking, this is crazy.
Jeez.
For those that live right in the middle of that line, is it going to be afternoon forever? Look how crazy it is to the person who lives right in the middle, gets out at night and goes to the day.
Oh, my God.
Very cool to live near that division. You get bored of the day, you go to the night. I wonder if there's someone who lives right in the line of the division between night and day. Must be nice to stand there between night and day, right at the division. Then you get to decide where you want to be. So that is Einstein of the week.
So basically, you can go in the front door in daytime and then come out the back door and you'll be in nighttime. Right.
Oh, but with a black
Yeah.
hole, maybe that's possible.
Yeah.
I don't know.
It is.
That's what's at the middle of the black hole.
So there you are. That's our weekly delve into the insanity of social media.
Well
In the
done.
middle of the halves,
Yeah.
well, that'd be midnight and noon, wouldn't it?
Yes, known as the event
Because
horizon.
Yeah, because in the middle of the halves, you'd be in midnight and at noon. So you're nowhere near the Terminator.
Oh dear.
Insane.
He'll be
Okay, gents, I got to leave you. I got to go teach my class, teach
Okay, then.
astronomy.
Teach them
Bye,
Black Night
Lou.
in Day.
Bye, Lou.
Catch y'all later.
See you later, Lou. Take care.
Take care.
Take care, Lou. Thanks a lot. All right. Yes,
Sure.
got a comment here. Let me just get this up. It says, I saw the Terminator, and the guy who was in my 8086 programming class came in at the end and was the manager of the movie theater. Oh, great. Okay. All right. We're going to finish off this evening in time on a fashion. We're going to do Constellation of the Week, if Roger's ready.
Yes.
Okay. Just give me a second. We'll get that up there for you, Roger. And what is the Constellation of the Week this week, Roger?
And tonight we will be seeing all about Canis Major, the greater dog. Not Canis Minor, the little dog.
No, of course.
I'll leave that one to Michael,
Yeah,
because
that's one from Michael.
he does all the little ones.
Yeah,
He
Which
does
is
the
absolutely
puppies.
no
He does the
reflection on him
puppies.
at all.
No.
No.
So we've got some stories here all about Canis Major and its different mythologies through different societies here. So it's one of the 48 constellations catalogued by Ptolemy in the 2nd century, establishing its place in classical astronomy and commenting to its importance in Western star lore. So we've got the Hunter's Companion. So I've got Orion the Hunter, and then we've got Canis Major, which is the dog from that. Greater versus lesser. So we've got its greater dog in Latin, distinguishing it from Canis Minor, the lesser dog. Both serve as loyal companions to the mighty hunter Orion. So there we go. So we've got the Greek legend, which is Laelaps. In Greek mythology, Canis Major represents Laelaps, the legendary hunting dog, still a dog, blessed by the gods with the ability to catch anything it pursued. The divine hound was destined never to fail in its hunt, creating fascinating paradoxes in ancient tales. And Roman mythology, it tells of a dog tasked with guarding Europa, the Phoenician princess.
Huh?
The faithful canine failed to prevent Jupiter's abduction of Europa, leading to its placement among the stars as both an honor and a reminder. So there. Who knew that? But Orion's faithful companion depicts one of the hunting dogs eternally pursuing the hare constellation Lepus across the night sky, demonstrating unwavering loyalty even in death.
Wow.
So the dogs were chasing after the Lepus, the rabbits. So some viewed it as a wolf, and others different mythical creatures, but the theme of loyalty and guardianship remained constant across different cultures. Excuse me. So here we have one of the earlier star charts of the formation of the constellation of Canis Major. So across the southern skies there. So we've also got Sirius, which in the winter period is the brightest star in the night sky, the dog star. So we have some history about that. Also known as Alpha Canis Majoris, and it's a magnitude -1.46, making it the brightest star visible from Earth. And it's 8.6 light years away. And
it's
derives its...
actually a binary star.
It is.
Sirius A and Sirius B.
Oh, right. Spoiler alert.
Serious.
Okay. So it derives from the Greek word Sirios, meaning scorcher, and is directly linked to the phenomenon known as the dog days of summer, when Sirius rises with the sun during the hottest period.
Really? I didn't know that. That's interesting.
Wow.
That's where it comes from.
Sirius, not Scorchio. That could have been good.
Yeah.
as we've already been pre-warned, it's a binary star system. I don't know who watched this show anyway. So yeah, so the is a type A1 star, Sirius A, and is approximately 25 times brighter than our sun, reaching 9,940 degrees centigrade, which gives it its characteristic blue-white hue. We've also, for quite a period, wondered why Sirius was wobbling, and then we managed to eventually discover that it was a binary. And it's known as the Pup, and it represents one of the first white dwarf stars discovered, and is in an incredibly dense stellar remnant packed roughly with the mass of our sun into an object no larger than Earth, making it one of astronomers' most fascinating objects. Now, recently, in the last few years, it was at its greatest separation from Sirius, so there was an opportunity to be able to observe it, but I don't know if many people were able to, because obviously you will need a good large aperture to get the resolution for the separation, but it has been noted. So the dog days of summer, which is how Sirius got its name from, so it's noticed that Sirius was rising just before dawn during the summer's peak, coinciding with the year's hottest period across the Mediterranean region. And many civilizations believe Sirius's helical rise added its own heat to the sun, creating the scorching dog days that marked summer's most intense period. So maybe that's how that has how the phrase became, I suppose.
Yeah.
Into more recent times. So today we know the correlation was purely coincidental. Sirius doesn't affect Earth's temperature. Maybe till next week's Einstein of the week. And however, cultural connection remains embedded in our languages and traditions. So, other notable stars in Canis Major. We have got Adhara, which is Epsilon Canis Majoris, and is the second brightest star, and it's 430 light years away, magnitude plus 1.85, and has become one of the most powerful sources of ultraviolet radiation in our local galactic neighborhood. Delta Canis Majoris, Reason, a yellowish-white supergiant, magnitude 1.8, and 1800 light years away. And its brightness represents one of the most luminous visible stars in the naked eye. And then we've got Beta Canis Majoris, Mersam. These are good. You'll be all asking questions about these in the quiz. This blue-white giant displays magnitude 2 and is roughly 5 light years away. Serves as a beta Cepheid variable star, pulsating with a period of approximately 6 hours, providing valuable insights into stellar physics. And then we've got VY Canis Majoris, but one of the largest known stars in the universe. This red hypergiant dwarfs our sun by extraordinary proportions. If placed at our solar system's center, it would extend beyond Jupiter's orbit. So, size matters. So we've got some of the stars labeled in part of the illustration here of Canis Major. So there we go. And some objects here that we have got in the, we've got M41, a bright open cluster, discovered in 1745 by Charles Messier as his 41st entry. It's got hundreds of stars approximately 2,300 light years away, and formed in a molecular cloud of roughly 190 million years ago. So fairly recent, really. And then we've got Caroline's cluster from William Herschel's sister, who helped to contribute vast amounts to the astronomy, and spans roughly 25 light years across and contains several notable red giant stars, along with the blue-white main sequence stars. So have a look out for those if you're into those clusters of stars. Okay, so we've, as I've just said, Caroline's cluster, which is roughly containing 80 stars there. More notably, we've got Thor's helmet, NGC 2359. I've not yet got a good enough image for that, but I'm working on it, although it doesn't exactly get too high in the night sky for
always
us
quite low.
at our latitude. So it can be a bit of a problem if you're not too good with your horizon in that area. But worth the view, and probably worth about 45 hours of exposure if your name's Tom.
It's on my list, Rod. It's on my list.
It's on your list, yeah.
On my list.
This year, this year it was absolutely hopeless with the weather to get anything from there. And then we've also got a little dwarf galaxy, which is approximately 25,000 light years away, and there's a small satellite gradually being torn away by our galaxy's gravitational forces. Poor thing. Never mind. So we've got some interesting things here from ancient Egypt. Egyptians revered Sirius as Sothdep, linking its heliacal rising to the annual Nile flood and marking their new year. This celestial event determined agricultural cycles and religious ceremonies, embedding the star deeply within Egyptian civilization and mythology. And then the Babylonians, they perceived Sirius as an arrow aimed directly at Orion, incorporating it into their sophisticated astronomical calculations. Their meticulous observations contributed to early mathematical models of celestial movement and prediction. And then the Dogon tribe of Mali, that's in Africa, possessed remarkable advanced knowledge of Sirius and its wife dwarf companion star. Have they been talking to Eric von Daniken or somebody? Understanding its binary nature centuries before European astronomers confirmed it through telescopes, suggesting sophisticated observational traditions. Or they've got very much good eyesight, or they've been visited.
Well, they originally was postulated that in their mythology they were actually in their past through their folklore, they were actually met a alien tribe which had sort of like lizard heads that came from Sirius, and this is how they gained the information of the second star. But that's all been debunked. This all came out quite a long time ago as a mythological, as a folklore thing. That the reason they knew about it is that they had, they were friends with these fish-like people who came from Sirius. So So take from it what you will.
Okay.
It does sound a bit Von Daniken.
So Canis Major hosts at least 10 stars with confirmed exoplanets, contributing variable data to understanding our planetary stellar information. These discoveries helped astronomers refine models of how planets form around different stellar types and masses. And particularly massive stars like VY Canis Majoris, these extreme objects provide insights into the final stages of stellar life and the processes that create the heavy elements essential for life. So worth having a look at, and let's see how they can find out any more information. So this is basically what we're going to go. So what people like, it's a winter constellation, so it's not the best time to look at it at the moment, although we are starting to see the winter constellations coming out through, but obviously during the winter time it will be a good time to have a look through at Canis Major. And that's all I can say about that for this evening.
Fantastic. Thank you, Rog. Thank you very much indeed, as always. And we'll have another constellation of the week, I'm sure, next week. So there we are. Okay, right. Well, listen, time has passed. Sorry, Derek. We've gone over the 2 hours, but we had a lot to get through tonight. We hope you've enjoyed our special about black holes. We are going to carry on with it next week because poor Daz has not had a chance to deliver his history of the study of black holes, which is really, really interesting. So we'll carry that over to next week, and obviously we hope you join us next week. And also, Sandra has requested more information about Uranus, Neptune, and Pluto. So we will definitely put something together on that for you, Sandra. Speaking of Pluto, when we in our Astro Radio days, we had Alan Stern as a special guest. And Alan Stern, in case you don't know, was the man that basically made New Horizons happen. The NASA probe that visited Pluto in 2015, the first and only. And the story of how he basically pushed the mission through when it wasn't going to happen, and it was his struggle to get New Horizons to happen. Very, very interesting story. In case I just happen to have here the book that he wrote about it, called, he and David Grinspoon, called Chasing New Horizons. Fantastic book about the history of the struggle to get the Pluto mission actually up and running and on its way to Pluto. Really interesting book. So what I was thinking was perhaps we can get in touch with Alan again and invite him back to have another chat about Pluto, because it's a few years since we spoke to him last, and obviously new data and discoveries about Pluto are coming out of the imaging from New Horizons all the time. So it might be kind of nice to get him back to talk to us. We'll look into that, definitely. But as far as more information about Uranus, Neptune, and Pluto, your wish is our command, Sandra. We'll definitely get it done. Not quite sure when, but soon, I promise. So there we are. Listen, I hope you've enjoyed, as I said, tonight's Black Hole special. I'd like to thank the team very much for putting everything together. And we managed to get it all together in a remarkably short space of time. So we hope you've enjoyed it. If you have, perhaps you would just do us the favor after we go off the air, just leaving a comment on the video on YouTube. And as I've said before, and I will continue to say, the more comments we get on the video, the better, because it makes us more noticed by the infamous YouTube algorithm, which means our videos get recommended to more people, which the number of comments on videos is one thing that it looks at to decide whether to recommend our videos to people. If we don't get any comments, the algorithm assumes nobody's bothered. So if you could just do us a favor, it doesn't matter what you say, just leave a comment on the video. Don't forget to subscribe as well. And also don't forget our Patreon page, where for just a few measly pounds a month, you get all the presentations that we deliver to you on Tuesdays. You get videos that we post on the channel. You get videos early that we post on the channel before they're actually featured on Space Oddities. And as a present for joining, we also give you two lovely 10x8 Astro prints to help you, for you to frame and put on your wall or put in the bin or whatever you want to do with them. So lots of goodies you get for just a few pounds every month here on Space Oddities. And the address, as always, is patreon.com/Space Oddities. That's patreon.com/Space Oddities. We're trying to build a community there, and it would be lovely to see you there. Thank you all so much for being here. We do appreciate it. Thanks to Daz and Roger and Tom and Lou, who has departed. Well, not in that sense, but he's not here anymore. He's had to go and teach. So mind you, he's getting on a bit. So anyway. So anyway, from all of us at Space Oddities, we'll be back next week with more fun and frolics from the wacky world of the universe. So until then, have a fantastic week. Take care of each other, and we'll see you next week. And thank you so much for being here and all your contributions, all your questions. It's been a lovely evening. We hope you've enjoyed it. We certainly have. So see you next week, basically. And keep looking. There you are.
You might see some aurora tonight, so look north.
Oh, yeah, absolutely. Look north. Might get an aurora. Fingers crossed.
Wasn't that an old TV news channel? Look north.
Yeah,
Look north, lad.